What's the one physics law that every single engineer, no matter their field, absolutely has to know? Is it Newton's laws? Maybe something from thermodynamics? Well, while those are all crucial, I'm going to argue for a law that's even more fundamental. One that governs everything from the tiniest circuits to the most massive bridges. I'm talking about the second law of thermodynamics. Now, hold on. I know what you might be thinking. Isn't that just about heat and engines? Yes, but it's so much more. At its core, the second law is about one simple, inescapable concept: entropy. Entropy is often described as a measure of disorder or randomness, and the law states that in any isolated system, the total entropy will always increase or stay the same. It never, ever decreases. Think of it like this. You can unscramble an egg, right? No. You can't put spilled milk back in the bottle. You can't put a demolished building back together perfectly. All of these are real-world examples of entropy in action. Things naturally tend to move from a state of order to a state of disorder. This isn't just a suggestion. It's a fundamental rule of the universe. So, why is this so critical for engineers? Because engineering is fundamentally a fight against entropy. We are constantly trying to create and maintain order in a universe that is actively trying to create disorder. Let's look at a few examples. For a mechanical engineer designing a car engine, the second law sets a hard limit on its efficiency. You can never convert 100% of the heat from burning fuel into useful work. A significant portion of that energy is inevitably lost as waste heat, increasing the entropy of the surroundings. This law tells us that the perfect, 100% efficient engine is a physical impossibility. Understanding this isn't discouraging. It's empowering. It allows engineers to set realistic goals and focus on optimizing within the real-world constraints of physics, pushing for designs that minimize that unavoidable waste. Now, let's switch to electrical engineering. When you run current through a wire, why does it get hot? That heat is a direct result of the second law. The orderly flow of electrons encounters resistance, creating random thermal vibrations in the atoms of the wire. This is an increase in entropy. This is why your phone, your laptop, and massive data centers all need cooling systems. Every heatsink, every fan, every liquid cooling loop is a battle strategy against entropy. What about civil engineers? When they design a bridge or a skyscraper, they are creating a highly ordered structure from materials like steel and concrete. But from the moment it's built, entropy starts its work. The structure is constantly being bombarded by wind, rain, and temperature changes, all of which work to break it down. Civil engineers have to anticipate this relentless march of entropy. They choose materials that resist decay, design structures that can withstand environmental stresses, and create maintenance schedules to repair the inevitable damage. A piece of software that's perfectly ordered and functional when first written can become messy and chaotic over time. As new features are added, bugs are patched, and different developers work on it without a unified plan. The code's internal structure, it becomes harder to maintain, more prone to bugs, and less efficient. This is a form of information entropy. Good software engineering practices, like writing clean code, using version control, and are all methods to fight against this digital entropy and maintain the order of the system. And let's not forget chemical engineers. They deal with reactions, mixing, and separations. The second law is at the very heart of their work. It determines whether a reaction will happen spontaneously. It dictates how much energy is needed to separate a mixture into its pure components. For example, desalination, turning salt water into fresh water, is a fight against entropy. To create that order, you have to expend a massive amount of energy, which in turn increases the entropy of the wider environment, usually by burning fuel. The second law dictates the minimum energy cost for that process. So you see, the second law of thermodynamics isn't just an abstract concept from a physics textbook. It is the silent, ever-present challenge that every engineer faces every single day. It's the reason things break, wear out, and become inefficient. It's the fundamental reason why engineering is hard. We can't defeat entropy. The universe won't let us, but we can manage it. We can build incredible things that hold back the tide of disorder, even if just for a while. It's the rule of the game we're all playing. What do you think? Is there another law you believe is even more fundamental to all of engineering? Let me know down in the comments. I'd love to hear your perspective. Thanks so much for watching, and if you found this interesting, consider subscribing for more deep dives into the world of science and engineering. See you in the next one.